continue our journey. Can you hear me, Kevin? You're good? OK. So looking at other side chains, so asparagine, I don't think there is anything special about this guy to worry about. So let's just skip it. Aspartate. First acidic side chain. So it, by default, it is deprotonated. It has a negative charge of 1 because the carboxy group, the carboxylate group is negatively charged. It's deprotonated. But and that's the first example of a protonatable side chain, things that can change their protonation state depending on the electrostatic environment. And that brings me to the discussion about pKa. Yeah, that's OK. OK, so then we have side chains. We have neutral. We have groups that have. OK, so most of the time we are trying to simulate the system at neutral pH, and then we have a standard pKa values. For example, for acetic acid, which is very similar to aspartate and glutamate side chains, the pKa of this guy is about 4. So now the pKa is lower than 7. 4 minus 7 minus 3. So that means the ratio of the protonated form to the deprotonated form is going to be 10 to the minus 3. So we have very, very small fraction of the protonated form. We have to make up our mind. What is the most representative form that we want to simulate? We can't have it both, right? Fixed charge, fixed protonation state. And again, I mean, because the ratio is 1 to 1,000, so in solution, these are the solution values for pKa. In solution, our best bet would be deprotonated aspartate. And that's what we have here, ASP, negatively charged, and there is a negative charge here, which is, of course, shared between these two oxygens at the end and the carbon that is connected to them. So if you look at this group here, so you can see this is the carbon of the carboxy group, and this is oxygen 1, this is oxygen 2. They have different atom names, but they're the same atom type, because chemically they are identical. The same charge, because this group can rotate. So you have to symmetrize the charge here. Can rotate, they should be identical. And yeah. So now it is possible that if you go inside the protein, this is solution. So if you go inside the protein, you have this aspartate sitting here. And now let's say there is, by chance, there is another group sitting here, another negative charge sitting here. And because of the presence of that negative charge, now you're not in solution anymore because of the electrostatic effect of this. Now suddenly the negative form of this residue becomes disfavored significantly. So you can have a shift of pKa. And if this shift of pKa is strong enough, maybe suddenly your pKa, the new pKa, we call it pKa prime inside the protein is now suddenly 8. It's possible. It might become, actually, if you put a positive charge here, the pKa is going to go low. If you put it next to negative fields, the pKa is going to go up, meaning that suddenly this ratio, instead of being 10 to the minus 3, now you're dealing with a situation in which the dominant species is going to be the protonated form because of the shift of pKa. So what are we going to do? So this is, we have two problems. First of all, we have to find out what are these sites at which we might have sort of significantly shifted pKa. And then the second step is that how we should treat them in terms of topology to tell the program that these sites are protonated. So 2 steps. So for the first step, there are some pKa calculators or estimators, I should say, out there. So ProPKA is one example. There is a H++. And there are a couple of other programs that essentially what they do, they go through the protein structure and then identify sites where you have aspartate, glutamate, tyrosines, histidines, very important in terms of pKa. And then they try both charged and uncharged form and see which one is more stable in a sort of random way. But because the problem is, if you have multiple sites, there is, of course, coupling between these sites. If you change the protonation state of one site, you will affect the protonation state of the other site. So you have to look at, if you have n sites, you will have, in principle, to look at 2 to the power of n different combinations, see which one is more stable for that particular conformation that you are looking at. So it's not possible to do it this way. They go randomly around and change protonation states of different sites at random, in a random manner. And if the energy is going down, they accept that change. If the energy is going up, they reject it and move on, and so on and so forth. So based on this kind of algorithms, they can give you an estimate of the pKa of different sites. So now what you can do is, OK, so I would usually do a couple of these. Maybe you can do one examination with this program, one other with this program, and see, are there sites? Most of the aspartates and glutamates are going to end up having similar pKa's to their default values, 4, 3.5, 4.5. You don't have to worry about them because they're exposed on the surface. There is nothing special going on. But you might have a couple of buried side chains that are in a very specific environment. 2 close carboxy groups happen a lot, actually, in potassium channels. You have this arrangement. So if you have those cases, then suddenly you see that in the log file of these programs, you see, oh, there is an aspartate that has a pKa of 9, for example. Aspartate 216, for example. So if that's the case, then I would usually load them in VMD, look at them, and see, OK, do I understand? Does it make sense? What is the reason? So if you agree, then you can accept this suggestion. And based on this suggestion, then you can come and ask the program using a patch that we will look at to change the protonation state of this aspartate to a protonated form. So this becomes ASPH, I think it's called. We use a patch that protonates this residue. So now for the case of aspartate and glutamates, it's not too bad. You know, pKa 4 is not too bad. For the case of histidine, it's going to be very tricky because, so let me come to histidine. Yeah, let me see. Let me go to histidine case. OK, so aspartate -1. The rest is nothing special here, except for this additional improper angle here. So cysteine, there is nothing special that we need to emphasize here. Glutamine, boring. Glutamate, similar to aspartate, only 1 carbon longer, exactly the same. But for the case of dihedrals, glycine is a little bit special because it has 2 hydrogens connected to C alpha. If we need to apply some patches, if it happens to be the first residue or last residue, we have to treat it a little bit especially. In terms of patching it, that's the only special thing about that. You can see that, you know, if you want to patch this guy, if it's the first residue and you want to patch it, use a special patch for glycine. Don't use the enter default. That's we specified. OK, here is the histidine. So as you can see for histidine, so the first residue name I have is HSD. Histidine in PDB is called HIS. But if you look at this topology file, there is no such thing as HIS. So what's the problem? The problem is that histidine has 2 tautomers and can have 2 different protonation states, right? So you can have the structure of histidine side chain. If you look at this 5-membered ring, so here is your C beta going to this back. When you have a double bond here, that is fine. You have 1 nitrogen on this location. So this is C alpha, C beta. You have the structure there, but I'm going to move it up. Therefore, I prefer to draw it C gamma, and then you have N delta. And then you have also C delta here. And then you have N epsilon and C epsilon. So now you can have, for a neutral histidine, first of all, the pK of histidine is 6.5, which is terrible. Very close to 7. The difference is not going to be 1,000 to 1. It's going to be like 2 to 1. So you have to still, because of the pKs being a little bit, 6.5 being a little bit lower than 7, I would go with the neutral form. That's the dominant species, twice as much in solution. So I'm going to go with the neutral histidine. But then there are two tautomers possible. You can have the double bond here and the proton connected here. And I wish I had a different color. Oh, yeah. I think I might have discovered different colors. And you can have the hydrogen here and the lone pair here. So you can have the black configuration, lone pair on one nitrogen, hydrogen on the other, or you can have it in the flipped conformation, in which case the double bond is going to be here, right? So these two types of histidines have two different names. This one that has the hydrogen connected to the N delta is called HSD. We use the red. And the one that has the hydrogen on the other side is called HSE. So these are the two types of neutral histidines. Now, if you have slight change in your electrostatic environment, suddenly your pK instead of 6.5 becomes 7.5. Then you have to go with the protonated form of histidine, in which you have two protons. Both nitrogens will have the proton. And then, of course, you will have a positive charge added to the system. So that one is called HSP. So this, you see, I mean, this is the most difficult residue in terms of protonation state. I think nature, by design, uses this residue where you want to have protonation, deprotonation reactions easily happening. So that's great, but it makes it very difficult to treat it using fixed charge models or fixed protonation state systems in our simulations. So now, what's the difference between HSD and HSE? For most exposed histidines, that's also true for aspartates and glutamides, when they can rotate, it doesn't make any difference. So these two nitrogens are more or less in the same position. If you flip the ring, the lone pair comes here, the hydrogen goes there, so you can form nice hydrogen bond donor interaction to one side, hydrogen bond acceptor interaction to the other side. But if you have buried histidine in a binding pocket, then it does matter whether you put the hydrogen here, electrons there, or the hydrogen there, electrons here. So in terms of maybe, let's say, if you have, in this case, if there is a carbonyl group next door that can nicely interact with this free hydrogen, and then on the other side you have a hydrogen, polar hydrogen, that can interact with this lone pair, so it seems that HSD is the perfect configuration for that binding pocket. So these kind of considerations are important because this might not be freely rotating inside the protein, so it makes a big difference if you place the right configuration for the lone pair and for your hydrogen. So what I would do, again, though this pKa, some of these pKa calculators even suggest what might be the position of the hydrogen. This becomes also the case when you're adding a proton to a aspartate, for example. You want to protonate that because you have a shifted pKa. Are you going to put the proton here, or are you going to put the proton here? So that also becomes the case for this case. So some of these programs make suggestions, but you can also visually examine your side chain, look at, let's say, VMD, show all the histidines, You see 90% of them are on the surface. You don't have to worry about them. And you can flip the coin and decide whether you want to use HSD or HSE for them. We use the alias command to tell the PSF gen, alias HIS to HSD or HSE. Every time you see HIS in the PDB file, that standard name for histidine, just use the topology for HSD or HSE, it doesn't matter. But then for the special histidines inside the protein, then I have to go in and see which one is the correct or the best choice. And then I go inside my PDB, find those special histidines, and use the 3-letter code HIS, change it to HSD, for example, or HSE, depending on what you decide. And of course, for those that the pK is very high, should be protonated, you just change them to HSP. Yeah? So you have to do this at the level of the PDB editing. So it is actually, it's a little bit more work, but, and of course, again, like everything else, so if you have protein conformational changes in your system, and now suddenly this domain moves, this negative charge is not here anymore, now suddenly your histidine wants to become deprotonated again, neutral. So this is something that we don't have. It doesn't happen automatically in conventional MD simulations. You can re-examine the situation. You can go through your trajectories and maybe repeat your PK calculations for every 1 nanosecond. Take a frame and examine it and see if something like that is happening, then you switch the protonation state. There will be some discontinuity in your force and everything, but this is one way of trying to deal with the situation. There are some methodology known as constant pH. In principle, every time you are doing a simulation, you are running it at a constant pH, pH 7 or 4 or 2. You compare the pK values with the pH, assign the protonation state according to that, and then you continue that. It is a constant pH kind of simulation. But what is established in the field as constant pH simulation is the kind of simulation that allows you to dynamically change the protonation state of certain sites. So like they keep checking using much more sophisticated methods. They keep checking what would be the favorable protonation state of various sites during the simulation for you. It becomes more expensive because you have to do this additional evaluation, but they can do that. So those are known as constant pH, or in short, CPH simulations in the field. Much more expensive, but again, I think if you have a site, you're really, that's the main question you want to ask about the titration state of that residue in the binding pocket, in the catalytic site, what happens to it when the substrate comes in, then you have to do this kind of calculations. Okay. Questions? So I guess by the end of today, nobody's going to believe in anything you can get from these classical simulations after all these problems. But I guess despite all these problems, maybe biology is too robust and we still can get some information. I mean, really the power of simulation is that sort of it keeps track of a lot of interactions at the same time, something that you cannot do in our head. So it's just computer can keep track of all these pairwise interactions at the same time, every time step, and take into account the effect of noise and fluctuations and everything. And you might see something interesting, and then you have to take it with big grain of salt and carefully examine it and couple it to other information you have and make sense of it. So it can actually provide a lot of hypotheses. It can bring you a lot of surprises that might be interesting, might be wrong, might be right. So it's then your job to decide to what degree you want to rely on that. All right, so that's, yes, yes.
So you've done simulations of ion transporters. And certainly the ions will change the pH inside.
Absolutely, absolutely.
So has it been a big problem? I mean, as you've done it yourself, has it just like
I mean, this is, again, I think I would like to, yeah, absolutely. I'm very concerned about some of the results. So the free energy curve I showed you very proudly yesterday after 1.5 years of huge calculations. So this is about phosphate binding to a binding site that includes histidine. So I have no doubt that as phosphate comes in and binds, the protonation state of that histidine should change. But I had no means of doing that. It would have taken another 3 years maybe. So right now, this is all I have. But I'm concerned we are trying to actually look at that binding site. But the same, I mean, every methodology, when you crystallize a protein, you can always argue, oh, this is the structure in the crystal environment. Is it the same as what you have in the cell? When you put it in the membrane, in the presence of other things? And the answer is, that's what I see in my crystal, right? To what degree you want to rely on it, believe it, up to you. So this is really the situation. So but there are serious approximations here, so we have to be always careful. But again, I mean, we compare the free energy to other things, and we see the difference. It matches exactly what was thought should be the free energy profile, exactly the same features. The numbers make sense. There is no hysteresis. So yeah, I'm sure it's not perfect, but yeah, so there is a lot of room for improvement. All right, so then, okay, histidine, neutral histidine proton on ND1. So then we have also HSE, where you have your proton on Ne2. The proton here, lone pair up there, we talked about that. And then you have HSP, which is the protonated histidine. If you have a higher pKa, then you go with this case where you have 2 protons and 1 excess charge. So that was about histidine protonation state. All these hydrophobic side chains, I don't think there is anything we need to talk about. Lysine is another long side chain. For some reason, proteins, the longest side chains in proteins are both basic side chains. If anybody has a clue why that is, why evolution decided that, the longest side chains are both positively charged. I don't know why, but there is nothing special in terms of topology here. Methionine, let's see, phenylalanine. Proline is another special case because of the arrangement of the backbone. In terms of patching it, you have to use a special patch for that. Otherwise, nothing special. And let's go to patches. I don't think there is. Oh, yeah, everything is residue. In charm parlance, everything is a residue, including water. Water is also a residue, tip 3. And these are the charges, atom names, and atom types. And in this case, you don't have any patching. So we specifically say if there is a water there, you shouldn't patch it. It makes sense. There are some other water names here. They are very similar. You see, they are there just to be compatible in case somebody uses this name or has used this name. They are there. But let me go actually to patches here. So calcium is a residue also, a single atom. Residue atom name and atom type are the same. Charge is clearly 2. Zinc, you have sort of monster residues like heme drawn here. I mean, if you develop a parameter set, we did that actually for this. You can publish a paper just on parameterization of something like that. Because it can take you months of calculations and fitting and testing and everything. So let me search. Yes?
Where in the potential profile do you put hydrophobicity? I mean, how do you account for hydrophobicity, which is it's a solvent?
So hydrophobicity, so what is hydrophobicity? Hydrophobicity is not an effect itself, is the lack of ability to interact with polar groups. So you don't have to explicitly have a term for hydrophobicity. If you have enough interactions between hydrophilic groups, they would automatically exclude your hydrophobic side chains. So if you have enough polarity for your hydrogen bond groups, water, everything, so they find each other, interact with each other strongly, and then they exclude the other guys, and we call them hydrophobe. They don't hate water, but they are not interacting with it strongly. That's why they are excluded. We call it hydrophobicity, right? So the nature of hydrophobicity is mostly because there are stronger interactions. Those guys hang out together, and they don't want to hang out with me. So I don't need to specify any explicit interaction for hydrophobicity.
Hydrophobicity is based on the entropy of the
Yeah, sure. And the entropy of this, yeah, so if you want to look at it, this is for the potential energy part, what we are talking. If you want to look at the entropy, yeah, of course. For entropy, I don't need to specify any potential energy. It's really based on the configuration of the system and randomness, right? So for that, this is all about potential energy, what we have here. So for that, you don't need any specific terms. So now let's go to patch. So this is a quite sort of, so if you want to change something about all the alanines, so then you go to the standard topology of alanine and change the charge or whatever you want to do. But now you might want to do post-translational modifications of your protein. Your protein has been synthesized and you want to just put phosphate on one side or do something special for one of the residues. Then you come in and use these patch residue commands. So what they do, exactly what I say, post-translational modification, they go in and work with an already existing residue and do modifications. So you have pres, enter, that's what is added to your protein by default at the first residue. So what is happening, so you just, you might introduce new atoms. You might change the atom type for an already defined atom. You might delete previous atoms. You might change the charges, et cetera, et cetera. So you can do changes here. But for a residue that is already inside your topology, inside your PSL file. So for example, what you do here, if you look at the residue that you want to patch with N-terminus patch, so you have a nitrogen, with a one hydrogen. That was how you use that block of alanine or arginine or whatever. And now you want to remove that old hydrogen. This HN is going to be removed. You delete that. And you're going to introduce 3 new hydrogens, HT1, HT2, HT3, terminal hydrogens. So you're going to introduce these new hydrogens. They have a special atom type. They're all charged heavily. They can form hydrogen bonds strongly. The charge on the nitrogen is going to be changed because you have a positive charge now at this center. And the charge on the carbon will be affected as well. So you're going to affect the charge on this one as well, et cetera. So you do all these changes using this patch command. Then in your whatever program you're using to apply these patches, you just say, apply this patch to residue number 217 or to residue number 1 in this case. So that's how you do that. So yeah, so that's one thing. So for glycine, as I pointed out, because again, there are 2 hydrogens here, so the treatment is going to be different. So we have a special glycine patching command. For proline is going to be special as well. You can, I don't like actually to use charged termini by default, because unless you have the entire protein sequence or protein structure in your PDB. So usually if you have the very first residue and the very last residue, in nature, in biology, you do have charges there. Good. But usually you have your protein sequence starts with 10 or 20. So you're somewhere in the middle of the polypeptide chain where you don't have a side chain, you don't have a positive charge. So therefore, I would prefer to leave it neutral. So if your protein, let's say, if your protein is very long, you have, I don't know, 20 residues at the end. The first residue is in solution. The 10th residue for which you have a structure is also in solution. Very far from the business end or business center of your protein, it doesn't matter. It doesn't affect, it's completely solvated. Even in that case, I prefer to have a neutral patch, not a charge patch. Not to introduce artificially a charge to a place where there is no charge in the real protein structure. So then this is one example of, you can acetylate their N-terminus. So you can add an acetyl group there, and that keeps it neutral. So I prefer something like this for the N-terminus and for the C-terminus if they are truncated compared to the real protein structure. So a bunch of varieties. Again, another type of post-translational modification or changes that you have in proteins. Oh, here ASP, not ASP-H. This is when you want to protonate some of your aspartates. You just apply this patch to that particular aspartate for which you calculated an elevated pKa or estimated a high pKa. So you apply this patch, and it's going to add the hydrogen and adjust the charges to get you the neutral aspartate. Same for glutamate. OK, so you can link. That can be useful to connect images. So this is, if you have periodic system, you want to repeat something, and it goes across the images. Maybe a more understandable link would be the disulfide bond here. So here you are applying a patch to 2 residues. So the only difference here is that now you will have these 1 and 2 preceding the name of your atom name, your atom name. So you see the C beta in atom 1 should be changed in terms of atom type and charge. The same for the residue 2. So you apply this patch to 2 residues, and then you delete the hydrogens originally connected to these sulfur atoms. And then you create a bond between the sulfur atom of residue 1 and sulfur atom of residue 2. So one thing to remember is that when you're creating initially your PSL file bonds and angles and dihedral angles are automatically generated, but here, after applying patches, they are not. So if you are creating new angles and new dihedral angles, you have to specify them explicitly. So by introducing this bond, now I'm creating 1 angle, 2 angles. That's it, right? 1 and 2 new angles. So these are the angles, 1 angle and 2 angle. And then I have multiple dihedral angles that go between, so it come 1, 2, 3 from here, and multiple residues there, across this bond and across this bond. These are all involving this new bond. So you'll have multiple dihedral angles created by this additional bond that you can. OK, so this is, I think, these are the most important parts. So yeah, so the concept of patches is good for applying some modifications to particular sites. OK, so now what happens if you use this topology file? So you have to, so right now we don't need the coordinates. It's just all about the topology and connectivity of the protein. So you don't even need to have a PDB. You only need to have the sequence of residues in your polypeptide chain or in every segment. You say, I have an alanine that is connected to a serine, to a asparagine, to an arginine, to a histidine. And then for each of these residues, the program, PSFgen, comes here, gets all the topology information, and dumps them into PSF for you. Okay? So residue 1 alanine. OK, here's the alanine information. 1 copy of alanine copied there. All the atom types, atom charges will be in the PSF. The next one is this. I'm going to add that, make the connection, and define everything there. Then you go to your water segment, do the same again and again. So all the information, all the topology information and charges will go into your PSF file. So let's look at the PSF file now quickly. OK. So now in the PSF file, we collect all this information, all the patching, all the modifications, everything will be here. So now we have a different format, no coordinate information. We don't have the XYZ, but everything else is now here. So we have a real index number here. It is created independent of what you have in the PDB. We have the segment name. Then we have res name, res ID. We have the residue name, atom type. We're going to need this for parameters. So these are the chemically meaningful kind of names. We have the charges, and we have the masses. All the information you need, except for the coordinates, are here now for to have complete information for the atoms, to be able to connect to the parameters that we will look at now shortly, and to have the charges, and to have the masses that you need for your MD propagation. So everything is here. So we start with the number of atoms. All the atomic information are here. Then there comes the water molecules. And then the next section is going to be about the bonds. Okay, so the next block, after introducing all the atoms, we have 5,117 bonds. It keeps track of these. And now that we have real indices here, we can refer to these as using their indices. Atom 1 is connected to atom 5. 2 is connected to 1. 3 is connected to 1. 4 is connected to 1. 1 is probably the N-terminus nitrogen connected to 3 hydrogens and the C alpha, for example. So we have exactly 5,117 bonds. So one way of, for example, if the simplest way of deleting a bond artificially would be to come here and remove a pair of these atoms, the bond that you want to remove. Or you can add an artificial bond here by adding 2 numbers here, connecting the 2 ends of your protein artificially by adding a pair of numbers here. Of course, for each bond, for each connection here, you need to have parameters also, because it looks, 1 is connected to 5. What was 1? That 1 is HT, for example. 5 is another HT. Now I need to have bond information parameters for HT connect. But for the case of dihedrals, we not calculate the energies and forces. That's how it goes. So then, as you can probably guess, the next step is angles. So now we have 4,197 angles exactly. So if you delete a bond, add a bond, you have to also change that number in the header. So now we have 4,197 angles. Now for each angle, we need to specify 3 atoms. 1 and 5 and 6 form one angle. 1, 5, 18, 2, 1, 5, etc., etc. So that's trivial. And again, for each of them, you need to have the parameters for the program to calculate the energies and forces coming from these potential energy term. 3,293 dihedrals, 1, 5, 7, 10 form a dihedral angle. These are the atom types. Give me 3 parameters I need for this term in the potential energy function to calculate the forces and so on. So all the bonds are defined, all the potential energy terms that we need, except for non-bonded that will be calculated based on a different algorithm. Everything is going to be in this PSF file. So now we need to have parameters. Let's go to the last file. Okay, so now in the parameter file, so now again, so we should usually use a parameter file whose name goes or matches the name of the topology. So again, you might remember we had TOP, all 27 protein lipid, top, and now we have the parameter file matching that. So that ensures that you are using the right atom type and the right parameters. They usually come in pairs, a pair of topology and parameter file. So we start with the section called bonds. Reminds you of the shape of the potential energy function. The potential of bonds, you need a force constant KB and B0 equilibrium value. This is a unit. In NAMD, units are always angstrom and kcal per mole. In GROMACS is kilojoule per mole and nanometer, so be careful about this. So now we have pairs of atom types. So this if you have a bond between C and C, force constant is 600 kilocalorie per mole per angstrom squared. B0 is 1.3350. And this goes on and on for every pair of atom types that you might have in your molecular system. So if you introduce an artificial bond between the two ends of your molecular system, then you have to make sure that that pair of atom type exists here, or you have to add that pair. In that case, I think you have an artificially long bond, like you can have a bond that is 35 angstroms long. That might be actually a way to bring the two ends together if you specify a shorter bond, and you can play with these tricks to do interesting things. So before I forget, I mean, I mentioned that you can play with the PSL file to introduce additional bonds, bond angles, dihedral angles. There are also commands, and Pawin, does it go to the configuration file, the extra bond command? Extra. Where does the extra bond goes? It goes to the configuration file of NAMD, right? In the configuration. So there is a command called extra bond, by which you can actually introduce additional bonds, bond angles, dihedral angles, without having to go through this PSL file. So what it does is essentially adding those terms directly to the PSL file. Still, you need to have the parameters for them. So you have the bonds. You can see the force constants, as we discussed, are around a few hundred kilocalorie per mole per angstrom squared. And then the next section is going to be angles. So another harmonic potential. And then we have 3 atoms forming a bond. And then we have K theta and theta 0, equilibrium value, and the force constant. Now you are in the tens, you see. This is a softer degree of freedom. So there is this Urey-Bradley term that some potential energy functions might use. So we have these additional terms here, so you don't have to worry about them for our discussion. So bonds are also specified here. So now if you build your molecular system, you have to do some atom typing. So you have to say, oh, this carbon looks like a carbonyl carbon. I'm going to assign a similar atom type to that. This nitrogen looks like a nitrogen in the backbone. I'm going to use the same atom type, in which case you will have all the parameters already here. But you might have to introduce new atom types for your drug, because you don't have anything that looks like that particular carbon in a ring in your drug. You don't have anything that looks like that. You have to do your own atom typing, and you have to make sure that all the bonds for that atom type are here, all the angles are present, et cetera, et cetera. So this, again, I mean, one exercise you do, a little exercise about this during the tutorial today. So then the next section is the dihedrals. All right, so we have now the dihedral angles here. That's the shape of the potential. You need K chi, and you have the N, and you have the delta. So you need 3 numbers for each dihedral set. So in this case, there are a couple of different features here. So first of all, for bonds and angles, you can only have one term for each atom set. You cannot have 2 terms for the same type of atoms. Doesn't make sense. But for the case of dihedrals, because you can have a kind of Fourier series of these with different n's and deltas and k's, really changing the shape of your dihedral potential, it is allowed to have multiple lines for the same set of 4 atom types. You have that sometimes, you can see. So the force constants are small, as you can see, compared to what we had above, in the ones or even fractions of ones, and you need 3 numbers. And then sometimes you can have wildcards, because the combination of these 4 atom types is very large. You have a large number of possible combinations, so they allow to use wildcards. Let me actually find a couple of examples. see if we can find something that looks, oh yeah, here. So look at these two. So they are the same 4 atom types. But then we have one main one, which has a very high force constant, 2.75, with a periodicity of 280 degrees. And then that's the main barrier, but they are doing a little bit of modification by having a second term, the small k, a different n, and a different phase to sort of modify the shape. For example, let's say cis and trans isomers of a double bond. So very sort of first approximation, they both have very low energy. If you have n equal to, they both have the same energy. But let's say you want to take into account that the trans might be slightly lower in energy. So you can add to this very large barrier rotation kind of dihedral potential. You can add something that has a periodicity of 1. It has a minimum at trans and a maximum at cis, but only maybe a half a kilocalorie per mole or 1 kilocalorie per mole barrier. So by combining these two, now you get something that still has 2 wells, but one of the wells is slightly lower compared to the other one. So you can combine these two to get something different. Or in one case, actually, what we did was really nice to, let's say, we wanted to look at a rotation, a cis-trans isomerization. That's exactly what we did. For the case of retinol in bacterial rhodopsin, we wanted to isomerize the chromophore after absorption of light. It isomerizes. And that's a very high energy state. So what we did was initially we had something like this. So this was the cis, and this was the trans. And we were, let's say, in the trans form all the time. Then we suddenly switched the dihedral potential, and we made this to be a barrier, to be a high energy state by introducing something that looked like that. So you switch the potential by changing the phase. Suddenly you make this transform, which was happy ground state, by absorbing, going to the excited state of the chromophore. Suddenly it became a high energy state. So now it wanted to go either this way or that way. They both end up with cis, actually. So now, but the transition was happening too fast. So like, we knew from experiment this should take about 200 femtosecond to take place, but because the high energy and a very large force we had there, this transition was happening too fast. So we use additional terms to introduce a little sort of well there in which the system stayed for a while before it isomerized. Some other Japanese groups did the same and call it Fujiyama potential. They're very good in names, huh? So anyway, so you can really play nice games with these dihedral terms if you want to sort of create particular dynamics or behavior. So I'm looking for an example of wildcards to show you. Again, by default, the program searches here. Here are the X's. So you search for, if you have a particular set of atom types, you search to find exactly that set, and then you adopt the parameters. If you don't find them, and you find something that matches that in the wildcard section, you know, the atoms in the middle, the bond in the middle, the atom types are here, then you can actually use the wildcard information for those. At least that way, the program doesn't crash. So there are some parameters. You need some numbers for that. So you see, for example, this guy here, it has a force constant of 0, K. That means it doesn't do anything to your potential energy. But the program requires a number for this combination. They probably added this just to have a neutral term there. Doesn't do anything to the potential energy or force. But it is there just to make sure that the program runs. Maybe they put all the dihedral barrier or rotational barrier into one of the possible dihedrals. So you have, let's say you have a bond, 2 atoms. Each atom is connected to 3 other atoms. That gives you 9 possible dihedrals. And instead of trying to distribute the rotational barrier between all of these 9 terms, maybe they were lazy and said, OK, let's just use one of these 9 combinations, one of the possible 9 combinations, put all the dihedral barrier there, and we put 0 for everything else. So that seems to be the case for these guys. So OK, so then these are the bonded parts, and then we have the improper section. Again, you have force constant, equilibrium value. Impropers are harmonic potentials. They are not cosine because they are not supposed to freely rotate. You just want to confine the center to a particular geometry. And then at the end, we come to the non-bonded section. So this is also interesting. So this is giving you some information how this non-bonded part of the potential has been fitted or optimized. So they are using a cutoff of non-bonding 12 angstrom and the switching function of 14 angstrom between 12 and 14. You're going to completely remove your potential. So we have to use similar conditions if you are using this set of parameters. Lennard-Jones, as I pointed out, so for Lennard-Jones, we have epsilon ij, and epsilon ij is defined as the square root of the product of epsilon I and epsilon j. So now we have to only specify this epsilon for a particular atom type, and then the program uses the combination rule to figure out the pairwise coefficient here. So we define this for individual atoms, the same for R mean. Epsilon I and R mean will be defined. So there are parts that are ignored. They are there for compatibility. So you can forget about actually the, see, C is the atom. This part is ignored. This is the epsilon. This is R min. And if there are additional terms here, they are ignored. So yeah, for the non-bonded part, essentially you have just the atom type, 1 epsilon value, and 1 radius value. So let's see, if there is something else. OK, so I think that's, so where is the, oh yeah, here. I'm looking for this. So at the end of the parameter file, there is another useful section that's called NBfix. So what it does is, so we know that these parameter sets are not perfect. And sometimes you want to actually adjust a particular interaction in your simulation system. For example, let's say we are talking about ions. We know that, so let's say I'm somehow setting up my parameter set using solvation free energy of sodium ions or potassium ions in water. So the interaction with water is good and everything. But then when this guy goes inside the protein in a particular arrangement of groups in a protein, then the interactions are too strong. This was the case, for example, for potassium channel, where you have a lot of carbonyl groups coming in, and you have a potassium in the middle. The interaction was too strong based on the behavior that we had for potassium. So then they had to modify this interaction, but only for carbonyl groups from a protein and potassium. They didn't want to touch anything that affects water-potassium interaction. So how can you do that? So if you change, the charge on potassium is fixed, is +1. There is nothing you can do there. The only thing you can adjust is the van der Waals, or the Lennard-Jones part of the potential. If you change the general Lennard-Jones potential, then it's going to affect everything, including water interaction. You don't want to do that. So what you can do is to come to the NBfix part. I don't have an example here. It says note lack of NBfixes even. But you can come here and introduce Lennard-Jones-like potentials, additional potentials that would adjust, either making them more attractive or less attractive, more repulsive. You can add these additional terms here to tune particular interactions between particular atom types here. And that has been used a lot for ion-protein interaction, even actually ion-water in some cases. So you can use some adjustment without having to go and change sort of core parameters in your force field. Okay, so I think, any questions so far? Yes?
So, so if I decide that a histidine, protein is going to be in a certain platination state, and I change that histidine name to something else in my PDB, so it will use this information. How does it know that?
Yes,
that
I mean, yeah.
these parameters?
Yes, I think you have to, so there is no patch for histidine. You have to, first of all, there are, let's call it, there is general histidine. There are, let's say you have 20 histidines. 19 of them, you have to do either HSD or HSE, and that you can use the alias command. In the PSF gen, you can say alias HIS HSD. That understands, okay, every time I have HIS, I have to use HSD. But then there might be one histidine that you want to use HSE or even HSP. For that single one, I think you have to go to the PDB and change the name of that residue to HSP or HSE in this example. So for aspartate glutamate, you can use the patches. We know which one should be protonated. You can specify what site, specifically or what sites should be protonated. That can be done using the patch command when you apply these patches at the end. Yes? Where? Or in the PSF gen, you mean a script, or what do you mean? I didn't quite understand. In the PSF gen. In the script, at the end, you can say, what's the command? Patch. Patch, and then the res ID, the segment name, and the res ID in that segment. And then you say the name of the patch you want to apply to that residue. Okay, so what are we going to do? So again, I think, so parameterization is not trivial. You can spend weeks. We try to make it simpler for you, but still it's a non-trivial task. And you need to know what you want to do. So there are two strategies for parameterization. One is doing it complete optimization, maximal optimization, and then minimal optimization. Usually you start with finding similar atom types from what is available, in addition to biomolecular kind of topology files and parameter files. There are lots of additional small molecule-oriented kind of parameters available. There is something called CGenFF, charm generalized force field, where you have a lot of chemical groups. So in most cases, you are able to find similar chemical groups for your drug, for your modified residue from that database already. You don't have to do everything from scratch. And then what you do is to, by analogy, you accept their atom types. Atom types take care of all the bonding information for you and the bond parameters. You don't have to worry about them too much. Non-bonded parameters, the van der Waals parameters are pretty much fixed because you are essentially dealing with the size of an atom that doesn't change much due to its chemical environment, so you're pretty safe to use them whatever there exists. But then the charges, you have to be very careful and maybe redo the charges. So, so we have the minimal optimization, in which you just directly adopt everything from some similar residues, including even the charges. And we have the maximal optimization, in which you have to go through all the steps, even calculate bonded parameters from second derivatives in your quantum mechanical calculations, and do all the fittings and steps. All the steps are streamlined a little bit in FFTK. So those of you who want to do parameterization in CHARM, I suggest that maybe this afternoon you can start playing with FFTK. So again, what FFTK does, maybe I'll come to that later. So it really depends on what you want to do. For the initial screening, for most cases, you are perfectly fine with minimal optimization, I would say. If you want to do really detailed free energy calculations, absolute binding affinities compared to experiment, probably you have to go in and do maximal optimization for your molecular system. I talked already about Alex's website, University of Maryland. So they maintain the force field. There is something called a string where you have a lot of additional small molecules parameterized by others and sort of somehow curated by Alex and his colleagues. So that's a good source to start with. You can always Google things to make sure that you're not repeating certain things. Some of the important aspects, I think I've covered everything. These are very important aspects about charge assignment and their ramifications. I mentioned it's very important. Different strategies in Amber based on ESP and in Charm based on interaction with water. We talked about that. Could be difficult. Lack of polarization. Several examples we talked about. Conformational dependence of partial charges. Try to be consistent with the force field, PK. I think we covered all of these. So these things are constantly under development. Again, as I pointed out, and I repeat, you always start working with a model compound, a small fragment, develop detailed parameters for that, and then you transfer them to the real big molecular system, hoping that they are transferable. So for example, in the case of lipids, let's say, so we have saturated tails, and then we have unsaturated tails. And what they did, so initially, when they developed parameters, these are the slides I got from my good friend and colleague, Scott Feller, by the way. I just want to acknowledge his work here. So initially, when they wanted to develop parameters for these, for these single bonds, what they did, they used this model compound, normal butane. 4 carbons in a row. You are interested in the rotation of a single bond in the middle. So you use this. You do a dihedral drive in your quantum mechanical program, and you get this nice symmetric behavior. So in the middle where you have a sort of eclipse of the two methyl groups, you get a high barrier, and the trans is the lowest energy configuration, and you have the 2 gauge configuration here. So that's fine. Then they use this to describe both single bonds in the saturated chain and also the single bonds in these guys, in the unsaturated tail. So note that lipids are not conjugated. You always have 2 single bonds between double bonds. They are not conjugated. So for these single bonds, they use the same model compound. But then they started doing some simulation, and they noticed, OK, so we go from this model compound to this real lipid system and simulating, and they started noticing there are some issues. And it's not behaving, it's not consistent with particular, with respect to particular aspects. It doesn't matter. Well, you see one example, actually. So then they said, oh, maybe our model compound wasn't quite adequate to capture everything about that molecular system. So what they did a few years later was actually, let's go to a model compound that is more similar to what we have here. So here we have 2 double bonds separated by 2 single bonds. So let's have the similar model compound here. 2 single bonds in the middle, flanked by 2 double bonds. And then at the end, I'm going to put 2 methyl groups to cap it. So when you do that, because of some specific electronic behavior, instead of this profile for a single bond rotation, you get this profile. Very different profile. So the barrier against the rotation is sort of similar, 4.5 kilocalorie per mole here, 5.5 kilocalorie per mole. It's not too different. But see, the width of these energy wells is much larger. And that means actually you're going to accumulate more of these kind of conformations You know, I mean, here you have a huge, very large conformation of trans here, minus 180 degrees. And then you have gauge, very steep kind of potentials rising on both sides. So you are accumulating the system in these very ordered structures. Here, you have in the middle 2 large barriers separating these two. But then, if you look at this side, there is a large exchange between these 2 wells from the side, very low barrier transition. You can go from here and come down here, right? So you can see actually much more flexible behavior for the same single bond based on this potential. So now, if you now go back and redo the potential and fit your classical dihedral potential to this sort of behavior by combining multiple terms for your dihedral potential, then you get actually much different behavior. So now they did that, and they are applying this to a lipid. So the blue one is a saturated tail where you have normal single bond dihedral potential, and then here you have the double bonds. This is a polyunsaturated tail of DHA. So, and you can see that results in a much more flexible behavior of this tail. So if you look at the displacement of the end methyl group in these 2 tails, you can see for the stearic acid tail is much smaller over a particular time, whereas the end of DHA diffuses much more compared to to the other tail. So you will end up with having a much more flexible unsaturated tail. That would affect actually its the way it approaches protein surfaces. They were interested in this case because this is the abundant lipid in for rhodopsin in retina. So, and they were interested how these lipids interact with rhodopsin and might affect the conformation or dynamics of rhodopsin. And when you do that, because that unsaturated tail is more flexible, it packs much closer to the protein. So if you look at the average distance between the protein and lipid, you can see that these unsaturated, highly mobile kind of lipids can pack more closely to your protein. So these are the radial distribution functions between the DHA polyunsaturated tail and the other tail of the lipid. So that can have actually major ramifications. So this is just one example of why we have 36 version of charm. They always go back to drawing boards, using better model compounds to fit the force field to particular behaviors. Maybe actually next year we discover another shortcoming of these force fields. We have to go back and use a different model compound to also cover that particular area. So it's a constant improvement sort of process. For the lipids, it's absolutely necessary to use the latest version of the, you should always use the latest version, but for lipids, we know very serious issues with the older versions of the force field, 32 plus. We have 36 now, Gio? 36A. Okay, I didn't even know about that. So we have the latest version of that. Rich Pastor, Bernie Brooks, and McCarroll have been working on some of the lipid-related force fields here. I mentioned polarizable force field. Benoit Roux's lab and Alexander McCarroll have been working on these. And now I would like to actually spend just 5 minutes maybe to introduce FFTK very briefly. So this is actually a toolkit that was developed by Christopher Main, a postdoc in my lab who worked really, who was a chemist actually, who came to the lab to do simulations on drug protein complexes. And after a few weeks, he got frustrated with how much work and how tedious it is to develop parameters. So he grabbed the TCL scripting book and read the whole thing and started programming. So with no programming experience, he became the best programmer of my lab, actually, in a few months. So he developed this first because he realized there are lots of difficulties. Again, there are lots of different strategies in terms of obtaining parameters. You can do this based on analogy. ParamChem is a good source to look at Swiss param and match. These are some examples of utilities that allow you to do this a little bit better. And then there are programs that allow you to develop parameters. And FFTK is one of the programs in this class. So what we do is, let's say this is a good example of a drug, acetaminophen, Tylenol, right? Or Tylenol is, yeah, Tylenol, right? So, so you have a drug, and then you might actually see how I can put together the parameter set for this drug. So let's say I recognize that I can, this one looks like a tyrosine side chain, so I might be able to adopt parameters, at least for the bonded part. I can get that parameters from the standard parameter set. This looks like N-methylcetamide, which is very similar to one of the patching residues that I already have. But then there is, of course, also coupling, so you can get some of the parameters here, some of the parameters here from two different molecules. And then we need to work on this, this guy in the middle, because it is now sitting between two different functional groups. This connectivity doesn't exist in the standard force field. We have to do something special about this fragment in the middle. So this, these are the three types of fragments that I have to work with. I have to work with something that looks like this guy in the middle, and I can look at this one separately, look at this one separately. This is just an example. In this case, you can really put everything together and treat. This is not too large of a fragment. You can treat the whole thing as one fragment. That's much easier. But just to give you an idea what we mean by fragmentation and working with fragments, you can calculate new charges for this moiety, a methyl group here, amino group, carbonyl group here. You can treat this separately. Then you have some new bonds for these bonds that involve these central groups. You have new bond angles that involve that group, and you have new dihedral angles. So you have to work with that. So in terms of how it is done, in FFTK, so you start with your PSF PDB. It gets actually prepares the system for you. It calculates the charges for you. And I go through the steps that are involved here a little bit. And then after that, it takes bonds and angle parameters for you, dihedral torsion parameters for you. And then it puts everything in the parameter file. So that's really helpful. So what are the steps involved here? So when you read the PSF PDB file, so it finds the missing parameters for you. So it tells you what are the missing pieces. You can immediately find out for what part of the system you need to develop parameters. Then it helps you with setting up the geometry optimization, QM calculations you need to set up, water interaction engine that allows you to create all the files. Then it generates all the input files that you need for these Gaussian calculations. You have to run the Gaussian job somewhere else. This is not a step that can be done interactively. So these are usually long jobs. You take all the input files, you run them somewhere else, and you bring the output files. And now it has a way to read the output files. If you use the same naming, it can actually parse the output files correctly, get all the charges from the files, and try to do and fit and optimize the charges for you between classical and quantum mechanical calculation. This is actually a major undertaking here. Can also set up frequency calculation for you if you want to do your bonds and angles based on Hessian calculations. So it sets up the calculation for you, run it, and bring back the output file of your Gaussian, and gets the output file and does all the transformation and mapping and everything for you. It also, so you see this is The strategy is we start with charge optimizations. So we get the geometry optimized, optimized geometry of the molecular system, use that to calculate water interaction and get our charges. That's step one. Step two, if you want to do the bonded parameters, now we do frequency calculation, Hessian calculation in quantum mechanical calculations and get the bonds and angle parts of the Hessian. The dihedral part is messy, lots of coupling between different. So you can't assign a particular frequency to a particular dihedral angle. There are lots of coupling there, so we can't get it directly from Hessian. But bonds and angles we can get, and this is something that FFTK does for you. Then for the dihedral angles, what you're going to do is you are going to rotate the dihedral angle and calculate the rotational barrier for that rotation, and then use that as the potential energy to which you want to fit your classical dihedral potential. Again, there is also torsional optimization. You have multiple dihedrals. How would you include all of them? How would you distribute all these barriers among multiple dihedrals? So that's also a sort of non-trivial step here. So it helps you to set up these torsion calculations in Gaussian with all the right keywords and everything. You submit the job, you get the output, bring it back here, and it reads the output and does the, yeah, okay, so let me, this in terms of the interface, what you work with, so it's, you have, this is the interface. So, I mean, your molecular system is loaded in parallel in the molecular visualization part of VMD, and you have all the fields. These are the tabs and the steps that you have to take and do. And then at the end, actually, it gives you, yeah, there are also utilities to constrain charges, you advanced setting, analysis of the fitting, how good your fitting is. So it's very powerful. There's a lot of work that has gone into this to simplify a lot of steps for you. So right now it works only with charm, but we are planning to also make it amber compatible. So if you want to do ESP charges instead of water fitted charges, you can do that. So this is just one example. You can see it is placing water at different sites, and then you just move the water back and forth and optimize their geometry, and then you do the dihedral torsions as well, and you try to do the fitting between all these multiple potentials that you get from QM and your classical description. So again, I think if you want to, you won't be able to complete it today probably, but I think it's a good idea. If parameterization is one of your main problems, maybe you can get started this afternoon, run into a few questions or problems. Those guys can answer your questions, hopefully, and get things started today. So, all right. Okay, so I think yeah, so there is a tutorial, by the way. So it says under development because my slides are old. The tutorial is available, so you can download that and look at it if you want. All right. Yes?
So the force field toolkit, we cannot use it with Amber, but when we are writing from scratch the parameters file, if we want to do it for Amber, basically will be like the charges will be different, and obviously we wouldn't be comparing it to water molecules. So like all of that part of all of that group, it will be a scratch. We'll be using just the residues and then different charges for Amber.
Yeah, I mean, if you want to do Amber, you want to do complete Amber for everything, or you want to just do charges based on Amber philosophy? What you want to do Amber simulations with the Amber force field?
Yes.
Okay, so then you just have to use Amber for everything. I think Amber force field is available in NAMD. You can say you want to use Amber.
Yeah.
And then you, for your new molecule, then you just do ESP charges based on Amber strategy, right?
Okay.
So there is no, you don't need this one. Not the water placement part. Again, I don't, for the, just give
I
me
meant
some.
for like the scripting when you have your PDV and your PSF, but you're trying to get your parameters then you will use the same thing minus the water molecules, and you will obviously the charges will be different. So you'll have to do
Yeah, sure. No, you don't use
water.
you don't use water at all.
Yeah.
If you're amber based, forget about water completely. I'm just wondering if FFTK can still be useful for you, because I mean, there is a coupling between charges and the torsional barrier, of course, because when you're moving a rotation, when you're rotating a bond, there are electrostatic interactions. So what charges you put here would affect your torsional barrier. Some of the barrier will be taken into account or accounted for by electrostatic interaction. So the charges should be fixed first, and then you see whatever is left, you would fit into your rotation, torsion. So you can put, I think you can put charges in. So so you can at some point when you have the charges, there is a place you can put in the charges. I want to put my amber charges there. I have calculated them, and now you do the torsion part only for me. So I think from that perspective, you can still use this. But I think your question is not about FFTK. You're just asking
no,
about.
It's like the first part of it when we were basically looking at the parameter files, and you were going step by step, like every residue with every charge
Right.
and everything
Okay.
else. Will have the same format, obviously, minus the charges will be different. But and obviously you won't have to put the entire input that has to do with water. So will the format as such will be the same for amber than for charm? That's what
I think so. I have never done amber simulation myself. I have to check, but I think the format is the same.
Okay.
Because the potential energy terms are the same.
Yeah.
It's just the charges and of course the parameter values that could be different between the two. But we can check. I mean, if you have something, we can check and look at it together.
Here, I can copy it from my
Yeah. So let's do it here. I have to leave at 1:45 to catch my flight tonight. So I will be around for another 1.5 hours. So yes.
So you said that FFTK will give you some of the missing parts in the game. If it doesn't have something, it will tell you that part is missing. So what should you do with that missing part?
Yeah, you have to. I mean, it sort of reads all the information. Puts them in a nice tabulated form. You can see what is missing, what is there. Do you want to accept it? Do you want to change it? You can even do it manually. So I guess, I mean, if you load it, it becomes more apparent what I mean. But then you have to calculate the missing parameters. So but at least you know what are the missing pieces, right? So it's a way for you to parse the information in the PSF, so you can see nicely now exactly what atoms are missing. And you can put them in by hand. Maybe you don't care, you want to put a number in it to get your simulation going. Just put one there just to get things going. You know, sometimes you don't care, you just want to have something running. It's a nice way to monitor what is happening. Is it ready for the simulation, essentially? Yes?
What are the parameter files used? Is it for generating the PSF or as part of the NB input? Or
The parameter files?
Yeah.
The parameter file is one of the inputs you have to give to NAMD. PSF has all the potential energy terms, what terms should be calculated, and then the values for those terms come from the parameter file. Yeah, so that's, you have to give it to as one of the inputs. Okay. All right.